All right, today we're going to tackle one of the biggest, most mind-bending ideas in all of science, Albert Einstein's theories of relativity. And this is so much more than just E equals mc squared. This is the story of how one guy's imagination completely tore up the rule book for how we understand space, time, and gravity. So how did he do it? Let's find out. Everything starts with just one question, a single what if. What if the universe had a speed limit? You know, a hard and fast rule that nothing, and I mean absolutely nothing, could ever break. This one little idea is where our entire journey begins. Because believe it or not, this one strange idea about a cosmic speed limit is the golden key that unlocks Einstein's first masterpiece back in 1905, the theory of special relativity. Okay, and right away, this is where reality starts to feel a little weird. Our everyday intuition just completely fails us here. I mean, look at the left side. It's totally normal, right? You're on a train, you throw a ball, the speeds add up. Makes perfect sense. But now, look at the right side. Light just doesn't play by those rules. It's a cosmic rebel. No matter how fast you're going, the light from your flashlight moves at the exact same speed, period. So, this whole mind-bending idea is built on two deceptively simple assumptions that Einstein put forward. First, the laws of physics work the same for everybody who's moving at a steady speed. And second, and this is the absolute game changer, the speed of light is the same for everyone. Full stop. Now, they seem simple enough, right? But just you wait, because the consequences of these two little ideas, well, they're about to turn our universe inside out.
Because here's the thing, if the speed of light is absolute, if it's the one thing that can't change, then something else has to. And that something else, well, it's just space and time themselves.
Okay, let's see how this works with a fantastic thought experiment. Imagine a light clock on a train. For a guy we'll call Bob, who's actually on the train, a little particle of light just bounces up and down between two mirrors. Simple. Tick, tock. But now, you're standing on the platform as that train whizzes by. From where you're standing, that light particle has to travel a much longer, diagonal path to hit the top mirror and come back down. So here's the big moment. If we both agree that the speed of light is constant, but you see the light travel a longer distance, there's only one possible conclusion. Time itself must be ticking slower for Bob.
This incredible effect is called time dilation. The faster you move through space, the slower you move through time. And this isn't just a fun idea, it's real. It means astronauts zipping around on the International Space Station are actually aging just a tiny bit slower than the rest of us down here on the ground.
And it's not just time that gets warped. To keep that speed of light constant for everyone, space has to be flexible too. Objects that are moving actually get squished. They get shorter in their direction of travel. What this really tells us is something profound. Space and time aren't separate things. They're woven together into a single fabric we call spacetime.
So what you have with special relativity is this beautiful set of rules that works perfectly on a flat, unchanging stage of spacetime. It's great for things moving at a constant speed. But Einstein knew his theory was incomplete. The stage was set, but one of the main actors was still missing: gravity.
And this was a huge problem, a showstopper. Because his own brand new theory, with its unbreakable speed limit, was in a direct head-on collision with Isaac Newton's law of gravity, a law that had been king for over 200 years.
I mean, you can just imagine this keeping Einstein up at night. If nothing, no signal, no information, nothing can go faster than light, then how does gravity work? How does the Earth instantly feel the sun's pull from almost 100 million miles away? It just didn't make sense.
You can see the clash right here. In Newton's world, if the sun just poof disappeared, the Earth would instantly fly off into space. But Einstein's universe says, whoa, hold on a second. We wouldn't even know the sun was gone for 8 minutes, because that's how long it takes its light to reach us. Gravity couldn't be instantaneous. The two theories were at war. One of them had to be wrong.
It took Einstein another decade of incredibly hard work to solve this puzzle. And the answer came to him in a sudden flash of insight, a moment he would later call the happiest thought of his life. And it was an idea that would completely change how we think about gravity forever.
And the thought was this: a person in free fall feels weightless. Just think about an astronaut floating in orbit. They're constantly falling towards the Earth, but inside their ship, they don't feel any gravity at all. They're just floating. And that feeling is exactly the same as floating in the total emptiness of deep space.
Now let's flip that on its head. Imagine a woman in a rocket ship, out in deep space, accelerating upwards. She feels a force pushing her to the floor. If she drops an apple, it falls. Now think about a woman just standing here on Earth. She feels her weight holding her to the floor. If she drops an apple, it falls. From inside their sealed rooms, their experiences are completely, totally identical.
This is what he called the equivalence principle. In a small, local area, you can't tell the difference between gravity and acceleration. They are two sides of the very same coin. And this was the insight that opened the door to Einstein's greatest achievement, the theory of general relativity. Because if gravity and acceleration are the same thing, then gravity isn't some mysterious force pulling things together. It's the shape of the universe itself. Mass and energy don't create a pull. They literally bend and curve the fabric of spacetime. And we're just traveling along the straightest possible lines through that curved space. The Earth isn't being pulled by the sun. It's following a straight path through spacetime that has been warped by the sun's mass.
So what this all means is that we live in a dynamic, geometric universe. The physicist John Archibald Wheeler put it perfectly. Spacetime tells matter how to move, matter tells spacetime how to curve. It's this beautiful cosmic dance.
And this isn't just a cool story. It's one of the most rigorously tested theories ever. It passes every test we throw at it. The GPS in your car only works because we constantly correct its clocks for time running faster in weaker gravity. That weird wobble in Mercury's orbit that stumped astronomers for centuries? General relativity explains it perfectly. We've literally seen starlight bend around the sun during an eclipse. And maybe most incredible of all, we've now directly detected gravitational waves, literal ripples in spacetime from black holes colliding billions of light years away. And the consequences are just staggering. General relativity predicts the existence of black holes, places where spacetime is so warped that not even light can get out. It predicts gravitational lensing, where giant galaxies can act like cosmic magnifying glasses. And it provides the entire framework for our modern understanding of the universe, the Big Bang, and its ongoing expansion.
So Einstein painted this magnificent picture of our universe as a smooth, curved geometry. But his theory breaks down at the most extreme places, at the very center of a black hole, or at the first instant of the Big Bang. And that leaves us with one of the biggest questions in all of physics today. What's next? What new theory, what new geometry will finally unite Einstein's universe of the very large with the bizarre, fuzzy world of quantum mechanics? That is the next great frontier.